Hello colleagues, my name is Zhang and I am from Xi'an, China. Let me introduce my experiment. I am following the instructions of Dr. Florian Metzler from the Massachusetts Institute of Technology. The experiment was conducted using Florian Metzler's plan. Describing first the experimental program at the Massachusetts Institute of Technology. MIT first proposed the theory of low-energy nuclear fission reaction, which is a major theoretical innovation. MIT's experimental program is to irradiate palladium or titanium metal targets with lasers in hydrogen or deuterium atmosphere, detect neutrons and nuclear fragments, to prove the existence of low-energy nuclear fission reaction. The experimental setup of the scene is shown above. The Massachusetts Institute of Technology and the U.S. Army Laboratory are at the same time to carry out research. The experimental setup looks very simple. In fact, is not complicated, is to use the laser to irradiate hydrogen or deuterium gas containers in the metal target. This is the schematic diagram of the MIT experimental device. The laser shines through the optical glass to illuminate the metal target in deuterium gas or hydrogen. The target is titanium or palladium. The container is equipped with two detectors, one for detecting neutrons and the other for detecting charged particles. The preliminary experimental results of Professor Jean-Paul Biberian show that laser irradiation of palladium in deuterium gas produces a large number of transmutation elements. Prior to this, Professor Ubaldo Mastromatteo's laser low-energy nuclear reaction experiment also yielded similar results. The following is my experiment. I read the experimental program of the Massachusetts Institute of Technology, MIT, and prepared to replicate the MIT experiment. I encountered a lot of problems in the actual experiment work, and the experiment is very difficult. I use a blue laser with a wavelength of 445 nanometers. The spot diameter is about 1 mm and the output power is 7 watts. I use 304 stainless steel to make containers, and K9 optical glass is used for glass. The titanium sheet is 0.1 mm thick and 20 mm in diameter. It is put into a container after being cleaned with alcohol. It is irradiated with a laser in hydrogen for 1 month. The picture shows the titanium sheet without laser irradiation and the irradiated titanium sheet. It can be seen that the irradiated titanium sheet has obvious light spots. County Route 39 adopts solid particle size detector made in Japan. The County Route 39 detector can only sense fast neutrons above 100 keV when directly measuring neutrons. This experiment only measures fast neutrons, and thermal neutrons are not measured in this experiment. After being calibrated by the Chinese Academy of Metrology with an americium-beryllium neutron source, the County Route 39 neutron capture cross-section used in this experiment is 1/2800th, that is, 2,800 neutrons can form a pit on the County Route 39 detector. The reaction cross-section of charged particles with vertical incidence in County Route 39 solid particle size detector is 100%. The etching process I used was 6.25 mol per liter sodium hydroxide solution, 85 degrees Celsius, etching for 4 hours, static etching without agitation, and washing with deionized water with agitation for 10 minutes after etching was completed. The etched County Route 39 can be observed and counted under the microscope. As you can see, the neutron imprint is smaller than the alpha particle imprint, so it's easy to tell the difference. I put the County Route 39 detector into the container, with the detector close to the inner wall and fixed with a spring. When the County Route 39 detector is far away from the laser point, neutrons and charged particles cannot be detected, and they're easily melted when it approaches. In this test, County Route 39 is 10 mm away from the laser point. Neutrons and charged particles can only be detected, and some detectors have slightly melted on the surface. I put titanium pieces and County Route 39 solid particle size detector into a container for fixation, assembled the container with the laser, connected cooling water, hydrogen, vacuum pump, and assembled the experimental platform, and then we can conduct titanium hydrogen laser experiments. After being filled with hydrogen and irradiated by laser, the experiment lasted for 1 month. After completion, the titanium sheet was taken out and sent to the Zhang laboratory of Xiamen University for SEMEDS detection. Take out County Route 39, and Turin laboratory will conduct etching counting to count the number of charged particles and neutrons per unit area. Based on the above measurements, it is calculated that the laser irradiation point can emit about 70 fast neutrons per second, which is a very small value and requires a long time to measure neutron imprints. The detection position is 10 mm away from the laser point. It is worth noting that if the neutron measurement distance of the laser point is greater than 100 mm, the measurement result will be close to the background value, and the number of detected neutron traces will be very small. Therefore, the measurement distance is very important. As can be seen from the above figure, the value of the charged particles is slightly higher than the background, and this result is slightly different from the expected one for 2 reasons. 1. The number of charged particles is not very large during the low-energy nuclear reaction, and 2. The detector position is on the side of the titanium sheet, and the charged particles are not scattered, and not much of them are detected on the side. I sent the titanium sheet after the experiment to the Zhang laboratory of Xiamen University for SEMEDS detection. The elements at the laser irradiation point are different from those without laser irradiation. The elements at the laser irradiation point have increased, resulting in new transmutation elements. As can be seen from the above figure, the number of neutrons and the distribution of transmutation elements are basically in agreement. The reason for the anomalous transmutation elements in the number 7 titanium sheet is yet to be investigated, and it can be proved qualitatively that the titanium hydrogen laser experiment has produced a nuclear reaction. The results of the experiment are summarized below. (1) The experiment verified for the first time the feasibility and reproducibility of the Massachusetts Institute of Technology, MIT, experimental program on low-energy nuclear reactions, and achieved direct and deterministic results. 2. The neutron values of the 7 hydrogen laser experiment containers were 1 to 2 orders of magnitude above the background value, and new transmutation elements were detected in the elements of 4 titanium sheets. 3. The values of charged particles in the 7 hydrogen laser experiment containers are slightly higher than the background values. 4. Container 3 and Container 7 lasers have decreased in power, resulting in lower values. 5. This experiment qualitatively verifies the objective existence of low-energy nuclear reactions. 6. Repeatability experiments continue. Thanks. Professor Peter Hagelstein proposed the low-energy nuclear fission theory, which is a major theoretical innovation. Thank you. Dr. Florian Metzler proposed an experimental design scheme, which can effectively verify Professor Peter Hagelstein theory. Experimental results prove that Professor Peter Hagelstein's theory is completely correct. If in doubt, you can send me an email. Thank you.
So, thank you very much. If there are any questions, any question? Yes, there is a question here.
Yes, Professor Zhang, I was wondering, I'm sorry, I missed it. What was your cathode material, please? Titanium. Titanium? Oh, okay. Thank you.
Any other question? So, Professor Zhang, thank you very much. Go ahead.
That's titanium too.
Good. Thank you very much. There's another question here.
Thank you for your presentation. Please, can you let me know if you are measuring or if you're planning on measuring the local temperature around or behind the spot that is affected by the laser? Local
测量
temperature.
温度这个事情比较复杂。
Measuring the temperature is more complicated.
我不知道剑桥大学的乔纳或者是麻省理工的弗劳瑞恩是否在现场。
Well, I don't know if Jonah from Cambridge or Frau from MIT were there.
如果他们在会场的话，可以帮我回答一下这个问题。
If they are at the meeting, they can help me answer this question.
我英语不是太好。
My English is not very good.
Thank you very much. We will ask Florian if he's here. Okay, thank you, Professor Zhang. Oh, another question? No. Thank you again. I'm sorry for the delays and the problems we had. Thank you very much again.